In this part of our calculus tutorial, we'll focus on integrals and integration. Let's begin with the basic question. How should we think about what an integral is? Well, there are two ways that we're going to discuss here. The first is we can think of an integral as, in a sense, the inverse of a derivative. They're effectively inverse operations of one another. For example, if you have a function and you take its derivative, then if you take the integral of that derivative, you get back the original function. Likewise, if you have a function and you take the integral of it, then if you take the derivative of that integral, you get back the original function. So in a certain sense, a derivative and an integral are inverse operations. They undo one another. A second key way of interpreting what an integral is you can think of an integral as a way of adding up a bunch of small things to get a total. And this approach and this way of viewing what an integral is turns out to be extremely useful in physics, and it arises in all sorts of contexts and problems. So we'll spend a bit of time focusing on that as well. By the way, in your high school math class, you probably were taught that an integral is an area under a curve. And that's true, but really we can think of that interpretation as the area under a curve as really just a special case of this more general view of an integral is a means of adding up things. And we'll see what that means in a little while. We'll begin this tutorial by focusing on what it means for an integral to be the inverse of a derivative. So let's examine what we mean when we say that the integral can be viewed as a type of inverse of a derivative. First, let's recall something about derivatives, a little bit of notation. If you have a function, f of t, then recall that we write its derivative with respect to t as df dt. Now let's look at the corresponding notation for integrals. Suppose I have a function, let me call it g of t, for example. Then I would write its integral with respect to t in this form. This is the integral sign, g of t dt. This is how we express the integral of some function g of t. Now, when we say that derivatives and integrals are effectively inverses of one another, what we roughly mean is that each one undoes the other. So let's look at a few examples so we see what that actually means. So suppose I have a function, for example, t cubed, and I take its derivative. I'll get 3t squared. If instead I had a function, for example, 8t squared, and I take its derivative, I would get 16t. If I had the function natural log of t, and I took its derivative, I would get 1 over t. So that's familiar from when we study derivatives. Now what we're going to do is turn this around. We're going to take each of these functions and integrate it. And that will, when we do that, when we integrate this function, it will bring us effectively back to here. When we integrate this function, it's going to effectively give us back this. And when we integrate this function, it's going to effectively give us back that. Let's be a little more specific here. Let's start with the first example. Okay, so t cubed, when we take the derivative, we get 3t squared. So now I'm going to grab this 3t squared and I'm going to integrate it. And this is so there's the function that I want to integrate, 3t squared, and here's our symbol for integrating this function with respect to time. There's the integral sign. We're integrating this function with respect to time. And when we do that, the result is t cubed. In other words, as claimed, when we integrate this function, we got back the original. Plus, this plus c represents some arbitrary constant. In fact, you don't quite get back the original. You get the original back plus some arbitrary constant. Let's look at another example. The second example here, if we have the function 8t squared and we take its derivative, we get 16t. Now I'm going to take this function, 16t, and integrate it. And when I do that, I'll get the integral of the function 16t with respect to time gives me 8t squared plus an arbitrary constant. So in other words, we effectively got back the original function over here again. Let's look at our third example here. The derivative of natural log of t is 1 over t. So now if we integrate 1 over t, we should get back natural log of t. So if we do that, this is what we get. The integral of 1 over t with respect to t is in fact the natural log of t plus this arbitrary constant. So more generally, think about what we're doing here. We're taking the integral of a derivative, right? So we had some original function, we took its derivative, and then we said, let's integrate that derivative. So we took the integral here of the derivative, and that gave us back the original function, plus some arbitrary constant. So it's in this sense that we can claim that taking an integral is effectively the inverse of taking a derivative. So if you've taken a derivative and then you take the integral of that derivative, you effectively undo the whole thing and you end up with the original function back again. By the way, knowing that integrals and derivatives are effectively inverses of one another, then that enables you to figure out lots of integrals. So for example, suppose I want to know what is the integral of the function cosine of t with respect to t. Well, if I remember my rules of derivatives, I may remember that the derivative of the sine function is the cosine function. So the integral of the cosine function must be the sine function plus an arbitrary constant. Okay, so once again, the idea here is that if you're trying to figure out the integral of some function, you can rely on what you know about the derivatives of functions. And since I know that the derivative of the sine is the cosine, therefore the integral of the cosine function must give me back the sine, because again, the integral undoes the derivative. I can check that I'm right, because if I take the derivative of this sine function, I should get the cosine function, which I do. Now, we've been looking at so-called indefinite integrals, but there's a related thing called a definite integral, and let me remind you about what that is. So a definite integral, first of all, it's written like this. It's very similar. It's the integral of g of t, of the function g of t with respect to time. But here we have two numbers that are at the bottom and the top of the integral sign, numbers a and b. And that's why this is called a definite integral, because of those numbers. So let me give you an example and show you how to actually compute with this. We've already determined that the integral of the indefinite integral of cosine of t with respect to time is just sine of t plus a constant. Now, suppose I don't want to know what the integral of cosine of t is, but I want to know what the definite integral from 0 to pi over 2 of cosine of t is. Well, it's very simple to compute. Here's what you do. First, you figure out the regular old indefinite integral of cosine of t. Well, we've determined it's this. Then you plug in, you replace t by the top limit here, pi over 2, and you'll get this. Next, you replace the indefinite integral here by 0, or replace t by 0, and that will give you this, and then you subtract those two quantities. In this particular example, when you subtract them, you end up numerically with 1. So let me repeat the general procedure here. When you want to compute a definite integral of some function, suppose you know what the integral, the indefinite integral of that function is. Take that value, the indefinite integral, and plug in, replace t by that upper limit there. Then replace t by the lower limit there, and then subtract those two quantities that you got. Let me give you another example to make sure you get a good feel for this. Suppose, for instance, I remember that the integral of 4t cubed is t to the fourth. Okay? But suppose I don't want to compute the integral of 4t cubed. I actually want to compute the integral of 4t cubed from t equals 1 to t equals 3. In other words, I want to compute this definite integral. How do I do it? Well, first I just look at the integral of 4t cubed, which I know is t to the fourth. Then I plug in, replace the t here by the upper limit. So I'm going to replace the t by 3. That will give me 3 to the fourth power. Then I go to the lower limit here and I replace t by that. That will give me 1 to the fourth, and I subtract them. And in this particular case, when I do that, it turns out to be numerically a value of 80. So that's the procedure for computing definite integrals. It's very straightforward, assuming that you know what the indefinite integral of the function is. Now, you may be asking at this point, well, what is this definite integral? What do these limits mean? How do they come from? How do you interpret them? Well, it's going to become much clearer what they mean when we look at our second interpretation of what an integral is. Previously, or currently, we've been looking at how an integral can be viewed as the inverse of a derivative. But our second interpretation of what an integral is it's a way of adding up a bunch of small things to get a total. And when we look at that second interpretation, then the meaning of what these limits of integration are will become much clearer. In fact, we'll see that when we're adding up, when we're interpreting an integral as adding up a bunch of little things to get the total, this tells us where we start, the point where we start the adding up, and this tells us the point where we end the adding up. But again, we'll go over that in much more detail. You also may have been wondering, when we write an integral, either an indefinite integral or a definite integral, in either case, we always have this thing like a dt here. So the integral of some function with respect to t is, we write it as here's the function, the integral of the function, and then we have this dt sitting here. Likewise over here. And what is this dt thing that's sitting here as part of the integral? What's its meaning? And again, that too is going to become clearer when we interpret an integral as a way of adding up a bunch of small things. And that's what we're going to turn to next, our second interpretation of the meaning of an integral. Just a quick remark before we get to that, though. I would just want to talk about different variable names. So for example, if I had a function f of t and I wanted to integrate it with respect to t, I'd take the integral, I'd write it like this, the integral of f of t dt. But if I was given a function that depended on a variable that I'll call x, and I want to integrate it with respect to x, we write it in this fashion, where instead of having a dt, we'd have a dx here. And likewise, if I was given a function h, and it depended on some variable y, so h is a function of y, then if I wanted to integrate it with respect to y, I would write it like this. Okay, so previously I was typically using f of t. We're given a function of time, but we can be given a function of some other variable as well, and we can easily express the integrals of those. Now we turn to our main point, namely how it's possible to view an integral as a means of adding up a bunch of small quantities. I'll illustrate with a series of examples. Our first example will involve finding the area under a curve. Suppose, for example, I plot a certain function. Here it is, y equals x squared, so we have a nice parabola. And I want to know what is the area under the curve between x equals 1 and x equals 3. So in other words, if I look at the area between these two curves, in other words, between the curve y equals x squared and the x-axis in this region between 1 and 3, so this area here, how would I find it? Now, I don't have a simple formula for it, so I've got to figure out some other method. And the method that we'll use is we're going to chop up this area into a bunch of thin little slices as follows. So notice here that I've chopped up this whole area into a bunch of thin little slices like that. Now, if I look at one of these slices, like this one here, it's sort of rectangular shaped. It's pretty much a rectangle on these three sides, and then there's a little bit of a curve there. But if I make these slices really, really thin, I can ignore like a slight curve there and just say it's approximately a rectangle. And so I know how to compute the area of a rectangle. It's just the base times the height. So if I just take the width of a given slice times its height, I can get the area of that one slice. And then if I do it for the next slice and the next one and the next one and so on, and I add up all those areas, starting from the rectangle here, that's near x equals 1, and ending at this rectangle here, near x equals 3, I will get the total area. Okay, so here's what we do now. Focus on one of these thin rectangles. Here I've shaded in one of those rectangles. Now this drawing's getting a little bit small, so let me zoom in a little bit so we can see, get a little better sense of what's going on. Now this rectangle that I just drew, it's located at some random position along the x-axis. So let me call its left edge, the location of its left edge, I'll call it x. It's just some random position, x. And the right edge of the rectangle is a little bit farther over, just a tiny amount. Now these are supposed to be really thin rectangles, so it's just a little bit larger, and I'm going to denote that as follows. Its x-coordinate is x plus, I'm going to call it dx. The quantity dx here that I just wrote is meant to represent the little bit over that I moved to go from the left edge of the rectangle to the right edge. In other words, dx is the width of the rectangle. dx is supposed to denote an infinitesimally small quantity. So I've drawn these a number of rectangles, and I drew them wide enough, thick enough so that you could actually see them. But what I want to imagine is that I'm drawing these rectangles. Each one is almost infinitesimally thin. And so the width of each one I'm going to note as dx. This dx is a symbol that represents this infinitesimally thin width of that particular rectangle. Okay, now let's look at the height of this rectangle. Okay, so we want to know its approximate height. Now again, the left-hand height and the right-hand height are slightly different because if you look at the top, there's a curve there, right? So the right-hand side happens to be a slight bit taller than the left-hand side. However, if the width of this rectangle that we're calling dx is very, very small, then the difference in heights, we can view that as negligible. So in that case, I'm going to say that this height here, the height of this rectangle, this distance here, is simply, well, since the rectangle is located at position x, then the height of this curve is just x squared. So the height of this curve is x squared. Over here, for clarity, I've just redrawn this rectangle, and its base, you see, is width dx. Its height is approximately x squared. So therefore, the approximate area of this rectangle, of that one little rectangle located at position x, is base times height. So I'll write it as x squared dx. And this quantity here, x squared dx, denotes the area of that one little rectangle. Okay, but I want to go through all these rectangles and add up their areas. So I want to take, so the basic idea is I want to take the area of a given rectangle, so x squared dx, represents the area of a rectangle located at position X. But I want to add up the areas of all these rectangles, from the rectangle starting at x equals 1 and ending at the rectangle near x equals 3. So here's the symbol that I'm going to use to denote summing all these rectangles up. There's the symbol. Oh, look, it's the integral symbol. And I want to sum up the little rectangles starting from the rectangle at x equals 1 and ending at the rectangle at x equals 3. And this expression here that we just derived will tell me the total area under this curve, because this integral symbol here means, think of it as, it means add things up. And what are we adding up? In this particular example, we're adding up the area under the curve of the areas of these little rectangles. So an integral sign, when you see an integral sign, you should really think you're adding something up. It's like a summation sign almost. Let's give ourselves a little bit more room to work here. Now remember, this quantity here, this integral that we constructed, represents the area under the curve here between x equals 1 and 3. So let's go ahead and evaluate this integral to actually see what the area under the curve is. Now how are we going to do that? Well, we have an definite integral here from 1 to 3. And so let's remind ourselves first what the indefinite integral is. So I may recall that the integral of x squared dx, I can write that as x cubed over 3 plus a constant. Now, where did this come from? Well, basically, I remembered my rules about derivatives in order to figure this out, because I remembered that the derivative of x cubed over 3 turns out to be x squared. So that's how I got it. So this is the indefinite integral, or in other words, the integral of just x squared. Okay, but we want to calculate the definite integral of the quantity x squared from x equals 1 to x equals 3. So let's go ahead and do that. Now let's remember how. The idea is that we take the indefinite integral and replace x by the upper limit here, namely 3. And so if we do that, that will give us 3 cubed over 3 plus a constant. Then we're going to subtract off the following. We're going to take this indefinite integral and this time plug in the lower limit, namely replace x by 1. So when we do that, we're going to get 1 cubed over 3 plus a constant. And now if I simplify this, this is going to give me 9 minus 1/3. And that represents the area under this parabolic curve between x equals 1 and x equals 3. Again, I want to reiterate that what the integral did for us in this example was it represented adding up something, and in this case it was adding up the areas of these little rectangles. But in other examples, we'll use integrals to add up things, but they won't be areas necessarily. We could add up anything that we want. So let's look at a few more examples to really get a good feel for this. In this next example, we're going to see how integrals arise when we try to find the location of the center of mass of an object. In this case, we're going to focus on a stick. Here's a stick, and we're going to assume that the length of the stick is L, and that the total mass of this stick is m. And so here I've just put down a coordinate system, so this end of the stick is at x equals 0, this end of the stick is at x equals L. And we want to find the so-called center of mass of this stick. Now, you may be thinking, wait a second, I don't know what center of mass is. That's okay. The point here isn't for us to learn all about center of mass, it's to show how integrals arise. So I'm going to teach you the one key thing that you need to know here about finding the center of mass of an object, and that will be enough for us to figure out where the center of mass of this stick actually is. So here's the only thing that you need to know about center of mass, at least for the time being. If you have a bunch of point particles that lie along a line, so here's a coordinate system, and I've put, there's a little particle of mass m1, it's located at position x1. Here's another little particle at mass 2, located at position x2 along the x-axis here, and here's a third particle, mass 3, located at position x3. And suppose I want to find the so-called center of mass of this collection of 3 particles. Here's what you do. You take the first mass and you multiply it by its horizontal position, x1. Then you add to it the second mass times its horizontal position, plus the third mass times its horizontal position, and then you divide the whole thing by the total mass, m1 plus m2 plus m3. So here, if you had 3 particles, this is how you find the center of mass. And if there are more particles than the one I've shown, maybe there are 4 or 5 particles, you would generalize this formula. I'd have, for example, a plus m4x4 plus m5x5 in the numerator, and I'd add plus m4 plus m5 in the denominator, and so on. Okay, so at this point, it really doesn't matter if you know why we're defining the center of mass in this way, where it came from, what its meaning is. That's not the point here. I just want you to accept that if you have a bunch of point particles all along a line, this is the method for finding the center of mass. You take the first mass, multiply it by its position, plus the second mass, and multiply it by its position, and so on, divided by the sum of the masses. Okay, that's all you need to know. Now let's go back to the original problem here, and here we have a stick whose total mass is m and whose total length is L. And we want to know where is the center of mass of this object. Now, we don't know how to find the center of mass of this object yet. All we've learned about center of masses is how to find the center of mass of a bunch of point particles. So finding the center of mass of a bunch of point particles like this is easy. We just plug in here. But how do we find the center of mass of an extended object that isn't just a single point particle, but it's an object made up of many, many particles forming a continuum here? So how do we do it? The idea is that we're going to take this stick and chop it up into a bunch of small little pieces. Each little piece will act like a little point particle, and then we'll use what we know about finding the center of mass of a bunch of point particles to figure out the center of mass of this continuous object. So here I've chopped the stick up into a bunch of tiny little pieces. Now I've drawn the pieces kind of wide. That's just so you can see them. You should really imagine that I'm chopping this thing up into tiny, tiny little slices. Each one is like infinitesimally thin, but I want to draw them big, as I said, so that you can see them. And the philosophy is I'm going to focus on a piece here and treat that piece as though it were just a regular particle, and then use what we know about finding the center of mass of individual particles to figure out the center of mass of this whole thing. So let me focus on one of these pieces. So let me grab one of these pieces. I'm going to shade it in here so you can see it. So I'm going to focus on that little section here. Okay, now this is an arbitrary piece. Let me say that the location of the left end of this piece is, let's say, at X, and the right edge of that piece is a little bit farther over, because remember, this is a tiny little piece. So I'm going to call the horizontal location of that right edge X plus a tiny little amount, which I'm going to note dx. So dx here represents a tiny little amount. In other words, it's the width of that piece. So if you like, I could say the width of that one little piece is dx. Now let me find the mass of that one little section of the stick that I'm considering. So I want the mass of that one tiny little piece. Now how do I do that? Well, I know the total mass of this stick is capital M. and I know the total length of the stick is L. So I want to use that information to find the mass of that one little piece of the stick. And that's pretty straightforward to do. Here's how we do it. The length of that one little piece of the stick is dx. The length of the entire stick is L. So this quantity here, dx over L, tells me the fraction of the stick that I have. In other words, the fraction of the stick that this little piece makes up. And if I take that fraction of the stick and multiply it by the total mass of the stick, that tells me the fraction of the mass contained in this one little piece. So the mass of that one little piece is dx over L times m. So I've chopped up the stick into a bunch of little pieces, and I found the mass of a given little piece. And this little piece that I looked at was located at position X. And so now I'm in a position to find the center of mass of the stick as a whole, because I'm going to view each little piece of the stick as just a particle. And so let's figure out how to find the center of mass. When we have a bunch of individual particles, this is what we do. We take the mass of each little particle times its position, and we add them all up. So let me focus on this particle. I'm going to take its mass, which is this quantity, and so let me write that as dx over L times m. That's the mass of one little piece, and then I have to take the mass of a given piece and multiply it by its horizontal position. Well, this little piece that we were considering is located at position X. So I take the mass and I multiply it by X. So this term here represents like one of these terms here. It's the mass of one of the particles times its position. The mass of one of these little pieces times the position of that piece. And now in the numerator here, we want to add up all those quantities, the mass times the position, for all the pieces, not just this one piece, but for the piece over here, starting at x equals 0, and the piece way over here at x equals L. And what does adding mean? It means doing an integral. That integral sign means adding. And what are we adding? We're adding up these quantities. And where are we adding from? We're adding from the leftmost piece at x equals 0 to the rightmost piece at x equals L. So we're going to get a definite integral from 0 to L. And then we have to, now to get the center of mass, when we had a bunch of point particles, this was the numerator. So this part corresponded to the numerator, and the denominator is just the sum of all the masses of all the particles here. Well, the sum of all the masses of this whole thing, we know it adds up to m, the total mass of the stick. So we divide by the total mass of the stick. Okay, now the main point here is that it's not that, oh, there's this magical thing called center of mass. I mean, center of mass is important, and we will talk about it in a little bit in a later tutorial. But what's important here is that this process of we wanted to add up a bunch of things, and adding up a bunch of things led to an integral. So this didn't really have anything to do with constructing an area under a curve. Integrals just mean you're adding something up. And so that's what we did here. Now, if we want to, we can complete this picture and evaluate this integral, and we can do that as follows. First, note that this mass here and this mass here cancel each other out, and so I can rewrite this integral, if I like, as the integral from 0 to L of 1 over L x dx. By the way, I've just swapped the order. Here I wrote it as dx times x, and here I'm writing it as x times dx. That's that's perfectly allowed. Okay, so now I want to evaluate this definite integral. Okay, so in order to do that, I have to remember what the indefinite integral is, and I happen to remember that. I remember that the indefinite integral of 1 over L x dx can be written as 1 over L x squared over 2 plus a constant. Okay, so now let's go back and evaluate this definite integral between 0 and L. So remember how to do that. What we do is we start by looking at the indefinite integral, and we replace the x that appears in here by the upper limit L. So that gives us 1 over L squared over 2 plus a constant minus, and now we're going to take this indefinite integral and replace the x here by the bottom limit, the lower limit here, 0. So that's going to give us 1 over L times 0 squared over 2 plus a constant. And if I simplify this, this turns out to be L over 2. So in this particular example, we found that the center of mass of the stick is located at L over 2. In other words, it's located exactly in the middle of the stick, halfway. And the center of mass, as we'll briefly talk about later, turns out the meaning of it is the point about which the mass is evenly distributed. So in this simple problem, the mass of the stick is evenly distributed about the center. That's why the center of mass came out to be at the exact center of this stick. But again, the main point that I wanted to emphasize here was not about finding center of masses, but rather how an integral represents adding things up. In the preceding example, we were adding up a bunch of tiny little areas to get the total area of something. And in this example, we were adding up a bunch of quantities, a mass times the horizontal position, and adding them all up to get the so-called center of mass. Let's turn to a third example. In our next example, we're going to find the so-called moment of inertia of a stick. So we imagine that we have a stick here. We'll assume that the stick has some length L, and that the total mass of the stick is capital M. Now, we want to find the so-called moment of inertia. And again, you might be thinking, wait a second, I don't know what moment of inertia is. That's okay. The point of this example is not to teach you all about moment of inertia. It's to illustrate how integrals can arise and how they can be interpreted as really just adding up a bunch of things. By the way, if you are curious as to what a moment of inertia actually is, you'll learn about that in your physics class. It has to do with when you rotate an object, the difficulty that you'll encounter when you try to cause it to spin. And what we're doing here is we're technically finding the moment of inertia of a uniform stick rotated about its center. But again, the point is not that we need to be experts at moment of inertia or anything like that. Now, there is one thing that we need to know about moment of inertia, and let me just teach you that. And once we know that one little bit of information, then we're good to go. So here's the idea. Suppose I have a bunch of particles lined up along a line here, and here I have the first particle of mass m1, whose horizontal position is x1, another particle, mass 2, whose horizontal position is x2, a third particle, mass 3, whose horizontal position is x3. I'm going to define the moment of inertia of this collection of particles about the origin to be the following. You take the first mass and multiply it by its horizontal position squared. And then you add the second mass times its horizontal position squared, plus the third mass times its horizontal position squared. And if you had more masses, you would just continue this formula. For example, plus m4 x 4 squared, and so on. Again, we're not going to go over what the true meaning of this is, but I just want you to accept that if you have a bunch of particles along a line, this is the procedure, the definition for finding the moment of inertia of those particles about the origin. Okay, that's all we need to know about moments of inertia, just this. And just based on this, we're going to be able to figure out what the moment of inertia of this stick is, which is really a continuous mass here rather than a bunch of separate masses. But the philosophy that we're going to employ here to figure out the moment of inertia of the stick is as follows. We're going to imagine chopping up the stick into a bunch of small little segments here. So here I've drawn the segments. As before, I've drawn these segments. Each one is fairly wide, but I want you to imagine that we've chopped this thing up into almost an infinite number of tiny little segments. So the width of each little segment, I want it to be infinitely narrow, infinitely thin, but if I drew it, you wouldn't be able to see it. So I've drawn them wide just so you can see it. And let's focus on one of these segments. And so here I'm going to darken in one of those segments. And the particular segment that I happen to be looking at, let's say its left end is located at position X, and its right end is located a little bit farther away at position X plus dx. So dx represents the slight change in distance when you walk from the left side to the right side. Or in other words, think of dx as the length or the width of that little segment. So our philosophy is we're taking this stick, we're chopping it up into a bunch of these tiny little segments. Each little segment is like a little particle. So we effectively have a bunch of little particles, but we know how to find the moment of inertia of a bunch of little particles. So that's how we're going to find the moment of inertia of this stick, through this chopping it up procedure. Now for each one of these segments, each one of these little particles, we're going to need to know the mass of the particle and its horizontal coordinate in order to construct the moment of inertia. So for each particle, we need to know its mass and its horizontal coordinate. And then we're going to add up these quantities, the mass times the horizontal coordinate squared for each of the particles. So we're going to do that for each of these particles. Okay, now let's start with this particle right here, which is located at position X. Let's start by finding its mass. We're going to use the same argument that we used in the preceding example. And let me just go through that again, though, so you have a little more practice with it. The mass of that tiny piece, that one little particle, we get as follows. We say, well, the length of that one little segment is dx. The length of the entire stick is L. So dx over L represents the fraction of the stick that we have. And if we multiply the fraction of the stick by the total mass of the stick, this tells us the mass of that one little segment. Okay, so now we know there's the mass of that one segment. And we also know that this particular segment is located at position X. So for that particular piece, we want to take its mass times its horizontal position squared. So we're going to find the moment of inertia, what we're going to do is take the mass of that one little piece, which we found to be dx over L times m, and we're going to multiply it by its horizontal position squared. And so for that one little piece, here's its mass, we multiply by its horizontal position squared. So we multiply by x squared. And this thing that we just constructed represents one of these terms for one particular mass. But we don't have just one mass here, we have a whole bunch of these little masses, a whole bunch of these little segments, starting from this little chunk here that's at position x equals 0, all the way to this chunk at position x equals L. And we want to add up the contributions to the moment of inertia from all these little pieces. So we want to add things up. How do we add? We slap an integral sign down because integration really means adding things up. And where are we adding from? We're adding from this leftmost segment that's at x equals 0 all the way to the rightmost segment at x equals L. And this quantity here that we just constructed is the moment of inertia of this stick about the origin. And once again, the main point that I want to emphasize here is how an integral, the way they arise in physics, is you're adding things up. You're adding up a bunch of little things. You have some object and you're trying to figure out one of its properties. In this case, the property is moment of inertia. And so we chop it up into small little bits and we calculate the moment of inertia of each one of those little bits, and then we add them up. That's what that integral sign means, adding it up. In the previous example, we were adding up something else to get so-called center of mass. And in the prior example to that, we were adding up something else, namely little slices of area, to get something else, the total area. But in all these cases, the general theme is when you want to, in physics, when you're trying to compute some quantity and it's kind of hard, you can chop it up into a bunch of small little bits, figure out the value of that quantity for that each little bit, and then add them up. And the adding process, that gives you integrals. That's what leads to integrals in physics. Now, just to complete this problem, so we work it through entirely, let's actually compute this integral. So we have the integral from 0 to L. Now I'm going to rewrite it slightly as m over L, the mass of the stick over the length, times x squared dx. So this is the function that we're trying to integrate. M and L, they're just constants, times x squared. And we want to take the integral between 0 and L. Okay, so let's remind ourselves how to do that. First, I remember that the integral, the indefinite integral of m over L x squared with respect to x is just m over L x cubed over 3 plus an arbitrary constant of integration. Now again, where did this come from? I got it by remembering my rules of taking derivatives. And I remembered that if I took the derivative of this expression, it's going to give me this, because remember, integrals and derivatives undo one another. So if you take the derivative of this expression, you will get that. You can verify that for yourself. But the point is, this is what the indefinite integral is. So now, to compute the definite integral, let's go ahead, and you remember our procedure. We take the indefinite integral, and we replace the x that appears here by L, the upper limit. So that gives us m over L times L cubed over 3 plus a constant. And then we do the same thing. We take the indefinite integral, but this time we plug in the lower limit here, x equals 0. And to write that out, that would be m over L times 0 cubed over 3 plus a constant. And if I simplify this, algebraically simplify this expression, I'm left with 1/3 ml squared. So, for what it's worth, this turns out to be the moment of inertia of a stick being rotated about its end point. Now it's time for you to turn to the practice exercises and try your hand at it.